Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 98, validate binary search tree. So in this video, we're going to share a solution based on recursion. So this problem actually is a classic problem. So here we want to make some remarks. So first, let's look at the statement. So given the root of a binary tree, determine if it's a valid binary search tree. So a tree is a binary search tree if it satisfies the binary search property. So the binary search property is specified by the three items here. And this definition actually is a recursive definition, right? So with that said, let's look at the examples. So example 1 is a BST, and example 2 is not. The reason is, for example, here 3 is less than 5. But 3 is in the right subtree of 5, right? So here the constraints are mainly on the number of nodes. The number of nodes in the tree is in the range 1 to 10 to the power of 4. So 10 to the power of 4 is a decent large number, I would say. And the node value is in between negative 2 to the power 31 up to 2 to the power 31 minus 1. In other words, a 32-bit integer. So with that said, let's look at the method we're going to share. So as we said that this problem actually is very standard. So the idea here is a recursion checker. So the idea is the following. For each node, we shall check its value is both an upper bound for each node in its left subtree and a lower bound for each node in the right subtree, right? So that's the full idea. So secondly, we want to make a remark before we write the code. So binary tree and binary search tree actually can be defined recursively. Actually, the tree data structure even can be defined recursively. Therefore, we could term them as recursive abstract data structures, or data types. So therefore, we could consider recursion when facing problems with them. So actually, you can see the videos for Leetcode 108. So actually, there are some comments or extensions on the problems that we can use recursion. So the plan for this video is the following. First, we are going to write a hyper function taking into bounds information to check BST. So this bounds is taking into consideration of the idea we specified in item 1. And then we prepare the return. So let's look at the code now. So actually the code is very straightforward and short. So first I'm going to write a recursion hyper function to check BST. So the function signature in this solution does not have the bounds information, so we can regard this one as a wrapper. So we can write a function with the bound information. So I'm going to write a recursor. So this is a checker for a binary search tree. So it accepts a root, and also accepts two bounds. So let's see, call it low and high. So the low is so I can write it here negative float infinity, so very small, and high to be float positive infinity. So this is the function signature, right? So then what we want to check is that, so if the bounds relations remained for every node or every subtree. So if first let's add a stop condition. So if not root, so we are going to return true, right? So this is standard. So next we are going to encode the bound information to the root. So first, if root value should be larger than the low, right, and smaller than the high. If this is the case, it's possible for this tree represented by the root to be a valid binary search tree. And also we need to check for its left subtree and right subtree. In other words, recursion comes into play here. So we are going to ask recursor root left. So for root left, the low is still the low, previous state, and the high actually is nothing but the root value, right? This is the one part, and then we need to check the right subtree. So root right. So the high is still the high, previous high, but the low actually is now the root value, right? So if these three conditions hold together, so we're going to return true. This means that the tree represented by the root is a binary search tree. So with that said, so we finished the first step, recursion hyperfunction to check BST. And secondly, we're going to return our result. So actually, we can regard this function signature just as a wrapper for this hyperfunction. So hyperfunction does the main job. So we'll just need to return a recursor root. So because we use this as keywords arguments. So with that said, let's do a check. So yeah, it passes the example 1, I guess. Now let's do the generic case check. Yeah, it passes all the cases. So I guess this is one full solution using recursion for this problem. One thing to notice that is that we shall check that for each node. So it's both an upper bound for each node in the left subtree and a lower bound for each node in the right subtree. Notice the two words each here. So with that said, I guess that's about it for this problem and for this video. Thank you very much.